Hello, my name is Terry Chen. I'm a Senior Application Support Scientist at TA Instruments. I would like to welcome you and thank you for joining me for this online training course. Our today's course is Part 1 for Rheology Theory and Applications. This section will be approximately 1.5 hours long. At the end of the course, we will give you a link to download the slides and also an email for asking questions. Here is the agenda for what we'll be covering for today. First of all, we'd like to introduce the basic theory of rheology, and then we're going to talk about what rheometer does, and how do we use rheometer to perform rheological measurements, and how to select the appropriate measuring geometry. After that, we're going to introduce all of the commonly used rheological test methods that you can use to measure your sample. Specifically, we're going to talk about how to design a flow experiment to measure the viscosity and how to design and set up an oscillatory measurement to measure viscoelasticity of your material. At the end, we're going to talk about how to design transient experiments such as stress relaxation or creep recovery. First of all, what is rheology? The fundamental definition for rheology is that rheology is the science of flow and deformation of matter. Specifically, rheology studies the relationship between a given deformation to the stress response of the material that's being measured. Then, what rheology measures? Rheology can be used to measure viscosity, elasticity, and viscoelasticity of a material. If your sample is a liquid and pourable, you can use rheology to measure its viscosity. If your sample is a solid, then you can use rheology to study its elasticity property. Most of the materials we're handling on our daily basis, they varied from liquid, cream, to semi-solid to soft gels. Those materials, they have both elastic response and also viscous response. In these cases, you can use rheology to study their viscoelasticity property. Then, how do we quantitatively describe a material's elasticity, viscosity, or viscoelasticity property? Back many years ago, there was a scientist whose name was Robert Hooke. He was the first scientist who developed the theory of elasticity. The model Hooke used was a spring. His observation was the stress he applied underneath the spring is linearly proportional to the deformation. From these research results, Hooke then defined the slope between the stress and strain curve as the Young's modulus of the spring. And this formula describes Hooke's law of elasticity. Later, in year 1687, another scientist whose name was Isaac Newton, he was the first scientist who studied the flow behavior of liquid material. The model he used was a dashpot. His observation was that the stress he applied to the dashpot is linearly proportional to the rate of the deformation. You can also call that the shear rate. From this research, Isaac Newton defined the slope between the stress and shear rate curve as the viscosity of the media that's in this dashpot. And this formula describes Newton's law of viscosity. Then what model we shall use to describe a material that has both elastic and viscous response? This slide shows two very basic fundamental models that people use to describe a material who has both viscous and elastic properties. The first model people use is to put one spring and one dashpot in serial. This is called a Maxwell model. This model is commonly used to describe a viscoelastic material's stress relaxation behavior. The second basic model that people use is called Kelvin-Voigt model. This model is by placing one spring, and one dashpot in parallel. And this model is typically used to describe a viscoelastic material's creep behavior. Next, let's talk about rheometers. How do we use a specific rotational rheometer to perform rheological measurements on your sample? At TA Instruments, we provide to our customers with two models of rotational rheometers. They are the Aries G2 rheometer and the Discovery Hybrid Series rheometers. These two model rheometers are designed slightly different, but they can perform the same typical rheological measurements to your different kind of samples. The Aries G2 rheometer has a separate motor and transducer design. The motor is built into the bottom of the instrument, which directly applies the strain to the sample. And the transducer is built into the top of the instrument that measures the stress that's generated from the sample. For Discovery Series rheometer, it is a single head design. Both motor and transducer, they are built into the head of the instrument. Motor applies the stress to the sample, and the optical encoder monitors the deformation that's coming from the sample. In addition to those two models, TA Instruments also provide to our customer a third type of rheometer, which is called RPA. This is a rubber processing rheometer, which is specifically designed and used for rubber industry to analyze the viscoelastic property of rubber material. Since this rheometer is using a separate software package, we will not be covering the application of these instruments in our today's course. So next, what does a rheometer measure? As we have mentioned before, rheology studies materials' viscosity, elasticity, and viscoelasticity. So a rheometer can provide the measurement on your material. It can measure your sample's viscosity. It can also measure your sample's viscoelasticity. A rotational rheometer can perform viscosity measurements as a function of time, temperature, shear rate, and shear stress. It can also perform oscillatory measurement and measure your sample's viscoelasticity. Specifically, will report as storage and loss modulus, tangent delta damping factor, and complex viscosity. It can measure those properties as a function of time, temperature, frequency, shear stress, and shear strain. The sample a rheometer can measure varies from very low viscosity liquids to semi-solids, soft gels, all the way to high stiffness, high modulus solids. One thing we would like to emphasize here is that rheology studies the relationship between a stress and a deformation. But the stress and deformation that's applied in the rheological measurements are both under shear conditions. Here are the formula to calculate in a rheological measurement how to calculate shear stress, shear strain, and shear rate, which is the rate of the deformation. From those parameters, you can then further define the material's modulus and viscosity. Modulus is calculated as stress divided by strain, and viscosity is defined as stress divided by shear rate, which is the rate of the deformation. However, in a rheological measurement, stress, strain, and shear rate are all calculated signals. The raw signals behind the scene are torque, angular displacement, and angular velocity. So when you perform a real rotational rheological measurements, your rheometer will either apply a torque, then measure the angular displacement and angular velocity, or the rheometer will apply an angular displacement with a certain rate and then using a transducer to measure the torque. So what is torque? Torque is a measure of how much of force acting on an object that causes this object to rotate. Here is the formula that defines the signal torque. Torque is one of the raw signals in a rotational rheometer. So when select to use one rheometers, you will know that particularly for this rheometer, there is a minimum torque and maximum torque the instrument can either apply or measure. Stress is calculated from torque. Here is the formula of how to calculate shear stress. Shear stress equals to torque multiplied by a stress constant. This stress constant is a geometry dimension dependent, depending on the size of the geometry that you use and also the measurement gap. When we discuss each individual measurement geometries, we're going to provide the formula of calculating this stress constant. The next raw signal is angular displacement. Angular displacement is the angle in radians for a rotating object that moves. In one full turn, the angle is defined as 2 pi, which is 6.28 in radians. So this signal is another raw signal in the rotational rheological measurements. This is directly either applied by the motor for Aries G2 rheometer, or it is measured using the optical encoder on the Discovery series rheometer. From angular displacement, we can calculate sample's shear strain. Strain equals to angular displacement multiplied by a strain constant. Again, this strain constant is also a geometry dimension dependent constant. When we discuss about each individual geometries, we will provide you with the formula for calculating this strain constant. Once again, we would like to remind you that in the rotational rheological measurements, the stress and strain are both applied under shear conditions. Even when you are measuring a solid material, you are applying a torsional deformation to the sample. Instead of, like in the DMA measurements, the stress and strain are applied in linear or bending deformation mode. Now, we have already talked about how to calculate shear stress and shear strain in the rheological measurements. Stress equals to torque multiplied by a geometry factor, and strain equals to angular displacement multiplied by a strain constant in geometry dependent factor. Then from here, we can further measure your sample's modulus. Modulus equals to stress divided by strain. The third raw signal in a rheological measurement is the angular velocity. Angular velocity is the change in angular displacement per unit time of measure. And here is the formula to define angular velocity. It is defined as radians per second. For people who are familiar with a viscometer measurements, you may be familiar with a unit called RPM, rotation per minutes. So in this case, one full rotation in radians is 6.28. So now you learn you can actually convert the angular velocity in radians per second to RPM. Then from angular velocity, we can calculate shear rate from this raw signal. Shear rate equals to angular velocity multiplied by your geometry strain constant. Now we have learned how to calculate stress and shear rate. From there, we can then further calculate the viscosity of the sample. Viscosity equals to shear stress divided by shear rate. When using a specific rheometer, you should always keep an eye on the instrument's specifications. Specifically, you will need to keep an eye on the instrument's torque range, the resolution for angular displacement, and what is the maximum velocity the instrument can rotate. This will help you with your experimental designs. In this slide, we're showing you with the specifications of the hybrid Discovery Hybrid Rheometer 1, 2, 3. In addition to shear measurements, this series of rheometers can also perform dynamic measurements, and here are the specifications for DMA mode measurements. This slide gives you the specification of Discovery Hybrid Rheometer 10, 20, and 30. And this slide is the specifications for using the ARES G2. ARES G2 rheometer is a high-end research-level rheometer. In addition to perform rotational rheological measurements, DMA measurements, the ARES G2 is also capable of performing orthogonal superposition measurements, which means this rheometer is capable of performing two-dimensional measurements simultaneously at the same time. It can perform oscillate measurements in the X-Y direction simultaneously also in the Z direction. Next, we would like to talk about geometries. How many different types of geometries you can use on your particular rheometer. Here is a summary of 4 typical types of geometries people commonly use in their rheological measurements. Among them, the parallel plate and conon plate are the most popularly used geometries in typical rheological measurements. They can be used to handle materials from low viscosity liquid, semi-solid, all the way to solid material. If you need to measure some really low viscosity liquid sample, the concentric cylinder with a cup and rotor geometry is more recommended. And here on the right side is the solid rectangular geometry. This geometry is commonly used to handle material with high stiffness and high modulus solid. With selecting an appropriate geometry, you can perform rheological measurement on varieties of different samples, varied from low viscosity liquid, which has viscosity as low as water or even lower than water, all the way to high stiffness, high modulus solid with modulus as high as a stainless steel. Depending on your sample's viscosity or modulus, you can always choose to use different sizes of geometries for your specific measurements. At TA Instruments, we provide to our customers with varieties of different sizes and different types of geometries. For example, here is a picture of all of the available cone and parallel plate geometries. From diameters, we offer to our customers with parallel plate that has a diameter varied from 4 mm all the way up to 60 mm. In addition to diameter, we also offer geometries with different surface texture. So the standard geometry has a smooth surface, but in certain type of measurements, if you need to avoid slippage in your measurements, you may need to use a roughened surface geometry. So here we will also provide to our customers with a sandblasted surface geometry and also a cross-hatch surface geometry. On the right side is all the varieties of different sizes of cups and rotors that we can provide to our customers, which can help to meet their specific measurement need. First of all, let's talk about the application of using a cone and plate geometry. The cone plate geometry is designed with this conical shape. At the center, it is truncated. So when using a cone plate geometry, you're not allowed to vary your measurement gap. Your test gap must equal to the truncation of your specific cone geometry. And the truncation size can be found from the shaft of that particular geometry. Cone plate geometry is commonly used to measure low viscosity liquid sample to a semi-solid sample. And here are the equations of calculating a cone plate geometry's strain constant and stress constant. Parallel plate geometry is more popularly used in general rheological measurements. And here are the formula to calculate the strain and stress constant in a parallel plate. Since the gap is used in this calculation, so that means when using a parallel plate geometry measurements, you can vary your measurement gap. The commonly used measurement gap in parallel plate testing varied from 0.5 mm all the way to 2 mm, depending on the viscosity of your sample. a parallel plate geometry can be used to measure sample from low viscosity liquid, semi-solid, soft gels, all the way to solid material. Since both Coulomb plate and parallel plate can be used to measure low viscosity liquid sample, then what geometry should I use? So let's talk about this. Here is a picture of a cone geometry design. Based on this conical design, when performing a shear measurements, a cone geometry applies a uniform shear from the center of the geometry all the way to the edge. So when you measure shear viscosity of a sample as a function of shear rate, you know that this cone geometry design provides uniform shear across your sample. Depending on the design of this parallel plate, sample underneath the plate does not receive a uniform shear. The shear at the center is 0, and the shear at the rim of the plate is reaching maximum. When perform a viscosity measurement, shear stress and shear strain in a parallel plate testing is reported at the edge. So therefore, if you use a parallel plate to measure a sample's viscosity, especially if this particular sample's viscosity is shear sensitive, you may see a slight variation for parallel plate results versus the results measured using a Coulomb plate. But these differences can be corrected back by using TRIL software. That is a very simple Rabinowitz correction, stress correction. The software will correct it back for you. There's also a limit of using a cone plate geometry. As I have mentioned before, when using a cone plate geometry, you are not able to vary the measurement gap. The gap must equal to the truncation height of your particular geometry. But look at the table here. If you're using a 1-degree cone geometry, the truncation height is only about 20 to 30 microns. So that means if you are measuring a sample that containing large particles with diameters about 10-20 micron size, you're not able to measure its bulk property. You're basically grinding the particles during the measurements. If you need to decide whether or not you can use this particular cone geometry to perform the measurements, usually the rule of thumb is that the gap, the truncation gap, must be equals to or at least equals to or greater than 10 times of your particle size. The concentric cylinder cup and bob geometry is also very popularly used for handling low viscosity liquid samples. Here is the picture to showing a cup with a recessed end rotor. This is one of the standard geometry that is used to measure the viscosity of a low viscosity liquid. Here are the formulas to calculate their strain constants and stress constant. If you need to handle some material that has extremely low viscosity, something like water or organic solvents like hexane or acetone, so here you can also consider to use a cup with a double wall rotor. This double wall design is further increasing the contact area between the liquid sample and your measurement geometry. This geometry will ensure to get better signal-to-noise ratio so that it allows you to handle extremely low viscosity liquid samples. And these are their stress and strain constant equation. For concentric cylinder cup and bob options, we offer to our customers with varieties of different sizes of cups and also all different shapes of rotors that can help to meet your specific research and measurement needs. The vein geometry and the helical ribbon geometry are typically used to measure things like dispersion or slurry kind of sample, and that geometry can help to avoid slippage during the measurement. Talking about measuring a solid material, the torsional geometry is commonly used. Here is a picture for a torsional rectangular geometry. This geometry is commonly used to measure sample in a bar shape. We also have torsional cylindrical geometry that also allows you to perform shear measurements. Those geometries are commonly used to measure high modulus, high stiffness samples. Here is the equation for specifically torsion rectangular geometry. In addition to this torsional rectangular and torsional cylindrical geometry that you can use on your rheometer to measure solid sample, your rheometer is also equipped with all commonly used DMA clamps. That allows you to be able to measure solid samples with different shape. If your sample is a film, you can use this film tension clamp. If your sample is a rectangular bar shape, you can perform the measurement using a 3-point bending or cantilever clamp. Torsional measurements applying the deformation under shear mode. DMA measurements applying the deformation in a linear mode. Even though they can both measure samples' viscoelasticity properties, the measurement results, especially the modulus, are defined in a different symbol. Shear modulus are defined as G, G prime, and G double prime. DMA measured modulus are defined as E, E prime, and E double prime. These two moduli are linearly related. They're following with this kind of linear relationship. And nu here is the Poisson's ratio of your material. Next, let's talk about experimental designs. How many different types of experiment we can design on your rheometer to measure your sample's viscosity and viscoelasticity. This first section here, we're going to talk about flow experiments. A flow test is used to measure the viscosity of a liquid sample. Anything that flows, you can use viscosity to describe their physical property. However, if you look at this table, you can see that the viscosity of different types of materials can be significantly different. Air flows, but the viscosity of air is extremely low. The viscosity of water at 4 degrees C is 0.001 pascal second, which is 1 centipoise. And the viscosity of an olive oil is roughly about 100 times greater than water. However, when talking about a polymer melts, silly putty, or an asphalt binder, the viscosity of this kind of material can be hundreds, thousands, or millions of times greater than water. So, selecting the appropriate test procedure and appropriate test geometry and parameters are extremely important in order to get the correct measurements for different samples' viscosity. For all liquids that flows, their viscosity behaviors can be categorized into two categories. They can be either Newtonian or non-Newtonian. The viscosity of a Newtonian liquid sample is independent of your measurement stress and shear rate. This kind of sample, their viscosity is only sensitive to the measurement temperature. A typical Newtonian behavior is commonly observed in a single component liquid, something like water, olive oil, or organic solvent. Most of the liquid samples we're handling on our daily basis are containing multiple components. The viscosity behavior of those kind of samples are non-Newtonian. One type of non-Newtonian liquid sample, they shows shear thinning behavior, which means for this type of sample, the viscosity is decreasing as you're increasing measurement shear stress or shear rate. Typical example for shear thinning sample include paint, lotion, shampoo, mayonnaise, or some pharmaceutical slurries. The other type of non-Newtonian behavior shows shear thickening behavior. For this kind of material, the viscosity is increasing with your measurement shear rate or shear stress. A shear thickening behavior is commonly observed in some highly filled slurry systems, like mud slurry or highly concentrated cornstarch. Now, let's talk about common rheological method for measuring the viscosity of liquid samples. In Trill software, when you select Flow Test Mode, from the drop-down list, you should be able to see a list of all the available test procedures you can use for measuring viscosity. Specifically, in our today's course, we would like to discuss in detail on 4 different types of common test methods They are single rate or single stress test, continuously rate ramp or continuous stress ramp, stepped or steady state flow, and the last one is measuring flow viscosity as a function of temperature. The first method is a single rate or single stress test. This is the simplest experiment you can program using your rheometer. A single rate test is an isothermal experiment. You load your sample to the instrument and hold it at an isothermal temperature. And then you program your instrument geometry to be rotated under a constant shear rate or shear stress. And then you perform the measurement as a function of time. This screenshot here actually provide an example of how to set up a single rate and single stress test using Trios software. If you have a Discovery hybrid rheometer and a single rate test method is named as peak hold. If you have an Aries G2 rheometer and this test method is called stress grow in Trios software. The use of this test method is providing a single point test measurement. It is pretty much like you are performing the viscosity measurement using a simple viscometer. And the second application for this test method is to scope the time it requires for the material to reach equilibration under a certain shear rate. Here is an example of a single rate test results. So this is to test the viscosity of a body lotion at room temperature with a shear rate of 1 reciprocal second. Specifically, we load the sample between a 40 millimeter parallel plate and we set the measurement gap at 1 millimeter. After the sample is equilibrated at 25 degrees C, we let the geometry rotate with a specific fixed rate at 1 reciprocal second. So at the beginning, you see the viscosity start to increase and then eventually it reaches to an equilibration. After the equilibration has been reached, you take a reading. That tells you the viscosity of this body lotion at room temperature and also at this particular shear rate is equals to 68.1 pascal second. The second flow method is a continuous ramp. This is also an isothermal test procedure. You load your sample to the instrument, and then you ramp your geometry shear rate or shear stress from 0 up to a certain value at a constant speed. For example, you load the lotion sample to a parallel plate and ramp shear rate from 0 to 100 reciprocal second in 1 minute. The application of this test procedure is to scouting the viscosity of a certain sample under a wide range of shear conditions. The other use of this method is to measure yield stress and thixotropy of a material. And this screenshot on the right side here is giving you an example of how to program a flow ramp experiment in Trios software. Here is an example of measuring the viscosity of a body lotion sample. We load the sample between a 40 millimeter parallel plate geometry, and then we're conducting a continuous ramp testing. Ramp the stress from 0 up to 200 pascal within 60 seconds. The viscosity that's measured as a function of shear rate is plotted in this graph. The reason we said this continuous ramp method can only scope the viscosity of a material, that is because based on this measurement design, we are not giving the sample enough time to reach equilibration before each data point is collected. Therefore, under low shear rate, you observe this phenomena showing viscosity increase as a function of shear rate, which is an artifact, because those data points were collected before the sample reached equilibration. However, under higher and higher shear rate, sample will require less time to reach equilibration. So those data collected under high shear conditions should be more or less correct. A continuous ramp experiment will provide you with a general idea about how this sample's viscosity looks like within a wide range of shear conditions. The second application for this continuous ramp procedure is to measure the yield stress of a structured fluid sample. In Section 2 of our Rheology Theory and Applications courses, we are going to spend more time to discuss in great details about what is yield stress and how many different methods we can use to measure yield stress. And here, continuous ramp is one of the test methods you can use to quantitatively measure the yield stress of a structured liquid sample. Instead of programming only one-step continuous ramp experiment, you can actually program a multiple-step continuous ramp up and ramp down test. For example, you can ramp shear rate from 0 to 100 reciprocal seconds in 1 minute, and then immediately ramp it down from 100 to 0 in another minute. The application of this procedure is to scouting the viscosity of a sample over a wide range of shear conditions. And another application for this procedure is specifically used to measure yield stresses and also quantify syncotropic index of a structured fluid. The screenshots on the right side here is showing you an example of how to program a flow ramp loop experiment in Trails software. Here is an example of using this continuous ramp loop procedure to measure the syncotropic index of a blue paint sample. Stress is ramped from 0 to 100 Pascal within 1 minute, and then it ramped down from 100 back to 0 within the same time. Syncotropic index is defined as the area between the ramp up and ramp down curve. Again, in our Section 2 of the Rheology Theory and Applications courses, we're going to spend more detail discuss about what is syncotropy is and how to measure the syncotropic index of different materials. The third flow procedure you can program using a rheometer is a flow sweep test. It is also called steady state flow. This is another isothermal test procedure. This flow sweep procedure allows you to precisely measure your sample's viscosity as a function of shear rate or shear stress. In this test, viscosity is measured point by point. The instrument starts from the very first shear rate, stays there for a certain amount of time until sample reach equilibration, and then take a reading, move to the second shear rate. Again, it equilibrates at this shear rate for long enough time until equilibration has been reached, and then take a reading, move on. With this method, you can guarantee that each viscosity data point is collected after the sample reaches equilibration. The screenshots on the right side actually showing you how to program a flow sweep experiment use Trails software. By checking on this steady-state sensing box, this allows you to use Trails software to follow a steady-state algorithm to ensure each data is collected correctly. Basically, this is how the instrument works. Once this geometry jumps to a certain shear rate, every 5 seconds, the software collects a data point. Every 3 data points, the software is making a calculation to see if those 3 data points are within a tolerance error of 5% or not. If those 3 data points are, the error among the 3 data points is too big, that means it's not under steady state yet. And then the software will collect another data points within the next 5 seconds. And then compare data 4, 3, 2 and see they are within 5% error or not. Until eventually the last 3 data points are within less than 5% error. In this case, the software considers that the sample is already reaching equilibration, and then it's going to collect data, move on the second shear rate. However, for certain type of sample, it may require extremely long time to reach equilibration. So therefore, the software gives you a cutoff time, which is called maximum equilibration time, which means if after 1 minute, okay, your sample is still not reaching equilibration yet, the software will collect the very last signal and put it in the data, move on to the next shear rate. after you finish your measurements, there is a parameter called reason for termination. If it says equilibrium, that means this data is collected under equilibration. But if that parameter shows time expired, that means that data is questionable. So that's because you max out the time in here, still not reaching equilibration. Of course, all of these numbers, the time for each data points being collected and the maximum equilibration time, can all be adjusted based on the operator's need. The second application for using this flow sweep experiment is to measure yield stress of a sample. This slide shows the viscosity of varieties of different kinds of materials. The viscosity of a corn syrup is high, but it behaves like a Newtonian because the viscosity measured here is independent of the shear rate. The viscosity of a butter lotion sample shows extremely shear thinning behavior. And the viscosity behavior of a polymer melt will show some Newtonian behavior under low shear conditions, but under high shear, it exhibits shear thinning behavior. The viscosity performance of a dispersion sample shows more complicated case. Under low shear, a dispersion sample may exhibit a Newtonian behavior. And then, in the moderate shear conditions, it shows shear thinning. But at high shear, up to a certain value, a dispersion material may also exhibit a shear thickening behavior. The last flow procedure we're going to discuss here today is a flow temperature ramp test. This is a flow test under a constant shear rate or shear stress. During the measurement, you are changing the temperature in a linear rate. You can conduct either a temperature ramp up test or a ramp down test. A common temperature ramp rate is varied from 1 to 5 degrees C per minute. The screenshots here is showing you an example how to set up a flow temperature ramp experiment. The application of this test method is to measure the shear viscosity of your sample under different temperature. Here is an example of measuring the viscosity of honey at different temperatures. The sample is loaded between a 40 mm parallel plate with a gap of 1 mm. Shear rate is set up at a fixed value of 5 reciprocal seconds. In the meantime, we program a heating test with a specific heating rate at 3 degrees C per minute. And the results is showing the viscosity of honey is decreasing as you're increasing measurement temperature. In this temperature ramp measurement, in order to avoid evaporation, you can consider to either use a solvent trap to cover the geometry and prevent sample evaporation, or consider use some silicone inert oil to cover the edge of the sample so that you can prevent sample evaporation. So far, we have introduced 4 commonly used flow procedures to measure the viscosity of liquid samples. Flow measurements are relatively easy in a rheological test. However, if you did not select the correct geometry or did not program the test using appropriate test parameters, very possibly you will be observed some artifact wrong results. Testing the viscosity of water is a very good example to showing you that if you did not select the right test parameter range, you may very possibly observe some artifact results. We all know that water is Newtonian. The viscosity of water should be around 1 centipoise, and the viscosity should be independent of your test condition, measurement, shear rate, or shear stress. However, this results showing that we're using 3 different geometries to measure the viscosity of water. Specifically, we used a 40 mm parallel plate at a gap of 1 mm. The second geometry we use here is a 40 mm 2-degree cone geometry. And the third is we used a concentric cylinder with a din rotor geometry to measure the viscosity of water at room temperature. The results shows that under low shear conditions, water behaves like shear thinning. And at shear rate greater than 200, water also shows some shear thickening behavior. So what is wrong with the low shear and high shear conditions? Since water has pretty high surface tension, under low shear, when the measurement torque is extremely low, the surface tension of water will drag some additional torque to the geometry so that it causes the measurement results to show some artifact. That makes like the viscosity shows higher value compared to the true viscosity of the sample. So this shear thinning behavior is caused by the surface tension of water. So then what happens under high shear conditions? When the shear rate is greater than 200, turbulence occurred. So when water goes into, when turbulence occurs under high shear conditions, the viscosity, the measured viscosity will show a higher value. That makes water looks like shear thickening. So in these cases, the only valid measurable shear rate to test the accurate viscosity of water is within this area for using a 40 millimeter parallel plate and Conan plate. So in order to obtain a wider shear rate range, the concentric cylinder DIN rotor with the concentric cylinder cup with a DIN rotor will provide you with the most widest range of shear rate you can obtain the accurate viscosity value of water. Another example case which will lead you to get artifact results is due to wall slip. Wall slip phenomena is often observed in flow viscosity measurements. Wall slip could either be caused due to surface wetting or due to wall depletion. When wall slip occurred, it will actually cause the measured viscosity lower than the true viscosity of the sample. It could also provide an artificially low yield stress measurements and also shows the sample behaves shear thinning earlier. One method you can use to diagnose whether or not you have wall slip during the measurement is by running the same experiment at different geometry gaps. If your sample does not slip, the measurement results at different measurement gap should be independent. Another method you can use to diagnose slippage is by testing the same sample using the geometry that has different surface texture. If the results are identical, you know the sample does not slip. Otherwise, slippage could be occurring during the flow tests. To avoid wall slip, you can consider to use a geometry that has a roughened surface texture. So at TA Instruments, we provide to our customers with a sandblasted surface geometry and also a cross-hatched surface geometry texture. In addition to use roughened surface parallel plate, you can also consider to use a cup with a grooved internal side surface area and in combination with a vein geometry or a helical ribbon geometry. Another factor which could also cause artifact results is due to edge fracture. Edge fracture is caused by the elasticity of the fluid. When shearing a viscoelastic material, a large normal stress difference can lead to a crack formation at the edge of the measurement geometry. This is called edge fracture. When edge fracture occurred, most likely your measured viscosity will be lower than the true viscosity of your sample. To minimize edge fracture in a flow experiment, you can consider to relatively decrease your measurement gap, or if you are an Aries G2 user, you can consider to choose to use this cone partition plate. When testing the shear viscosity of a polymer melt, both edge fracture and wall slip will occur during the measurements. This will limit your test shear rate to go no higher than 1 reciprocal second. In this case, you are really not able to conduct much of the shear measurements to measure viscosity of a polymer melt up to higher shear rate. In this case, you can consider to use an alternative solution, which is called Cox-Merz rule. Cox-Merz rule is an empirical relationship. it was observed that in many polymeric materials, especially under polymer melts, the steady shear viscosity plotted against shear rate is one-on-one correlated with the complex viscosity plotted against the measurement frequency. So in this case, instead of conducting a flow measurement to measure viscosity, you can perform a dynamic frequency sweep test to measure the complex viscosity versus frequency. And then through Coxemer's rule, you are able to obtain your polymer melts information, the viscosity information, as a function of shear rate. Then the question is, how do I know if Coxemer's really works for my particular sample? The way to prove that is by conducting two separate tests. The first test is a traditional flow experiment, which is shown in this graph. It shows in the red curve. You started the steady state flow measurements starting from extremely low shear. From the measurement results, you see that when the shear rate is greater than no more than 1 reciprocal second, edge fracture occurred, which caused the rest part of the data not being correct. So then you load the same sample. Instead of conducting a flow experiment, you're performing a dynamic frequency sweep test. From the results, you measure sample's complex viscosity versus frequency. Then, through Coxemer's transformation, you convert the complex viscosity to shear viscosity and convert frequency to shear rate. From there, you overlay your true steady-state shear viscosity results versus your converted results. If you are able to get a reasonable overlay under low shear conditions, that tells you that Coxemer's rule is working well with your particular polymer sample. If any one of you who is interested to learn more about how to avoid getting artifact results in the rheological measurements, then I would highly recommend you consider log on to TA Instruments website and taking this free webinar given by Professor Randy Eward. Randy also has a really good review paper which is posted in his website regarding experimental challenges for rheological measurements, how to avoid to get bad data. After you finish a flow experiment, you can consider to fit your flow viscosity curve to one of these flow mathematical models. Here is a list of all commonly used flow models that people use to fit their viscosity curves. All of these models are available in our TRIO software. The benefit of fit your experimental data with one of these mathematical models will allow you to extrapolate and calculate the material's zero shear viscosity or infinite shear viscosity. The other benefit will allow you to mathematically calculate the viscosity of your sample at a specific shear rate condition, which may not be is one of the data points in your test procedure. Here is an example of fitting the viscosity curve with one of the flow models. The viscosity of this blue paint is measured over a wide range of shear rate. After the test is finished, we're fitting this flow curve with the Karu-Yasuda model. From this model fitting, it allows me to extrapolate and calculate the zero shear viscosity of this blue paint. This gives me a good information that helps me to correlate with the sample's storage stability. Also, from this Karu-Yasuda model fitting, it gives me some information about the viscosity of this blue paint under infinite shear rate conditions. Where can we find those model equations? When you get onto TRIO software, look for this big question mark. Click on this question mark will activate the online TRIO's help menu. From the help menu, if you type in keywords flow models, then the menu will give you a list of all the mathematical flow models that's available in TRIO software. And then if you click on Karu-Yasuda, here is the equation for this mathematical model. From the model, you can calculate zero shear viscosity and also infinite shear viscosity. Now we have finished discussing all flow procedures for viscosity measurements. In the next section, we're going to discuss the oscillatory test method for measuring the viscoelastic property of a material. Not everything flows. Taking water as an example, at room temperature, water is a liquid. It has really low viscosity. So of course, you can use viscosity to describe its physical behavior. But if you cool down water, water will freeze into a solid. It becomes ice. Ice has really high modulus. It's a purely solid material. So in this case, it is inappropriate that you use viscosity to describe its physical behavior. Another example is silly putty. If you put silly putty onto a surface, over time, silly putty will gradually flow flat based on its own gravimetric force. But if you make silly putty into a ball and hit the ball against a surface, silly putty will bounce like a rubber. So this tells you that silly putty can behave like it's a semi-solid material. It can have both viscous behavior and elastic behavior. So what kind of method we shall use to measure the mechanical property of a solid or a semi-solid material? In rheology, the dynamic oscillatory tests are the typical method to evaluate the viscoelastic properties of a solid or semi-solid material. In an oscillatory test, the instrument applies a sinusoidal strain to the sample at a specific frequency, and then it monitors the sample response in stress. If your input sinusoidal strain is under a small amplitude which never irreversibly changed your sample's microstructure, then your sample's response in stress should also show a sinusoidal waveform. The shift between the input strain signal and the output stress signal is defined as the phase angle of your material. When testing an ideal solid sample, which is purely elastic, the phase angle is 0. When testing a purely liquid sample, which is completely Newtonian, and then the phase angle should equal to 90. For most of the materials we are testing here, they have the phase angle should be in between 0 to 90. If your sample is more solid, you should observe the phase angle that's close to 0, which is small. If you're testing a very liquid sample, which has lower viscosity, and then you will observe a large phase angle, which is close to 90. Here is a list of all common viscoelastic parameters you will obtain through a typical oscillatory test. The first parameter is called complex modulus. Complex modulus is a measure of a material's overall resistance to a deformation. Complex modulus is defined as the sinusoidal stress divided by sample strain. This modulus can be separated into two components. The first component is called elastic modulus. People also call that storage modulus. It is a measure of the elasticity of the material, the ability of the material to store energy within the oscillation cycles. The second component is called viscous modulus. People also call it loss modulus. It is a measure of the ability of the material to dissipate energy, how much energy is lost as heat during the oscillation measurement. Another parameter is called tangent delta. People take the tangent of the sample phase angle and use this parameter to describe material's damping property. Tangent delta is defined as loss modulus divided by storage modulus. Another common parameter you will see in an oscillatory test is called complex viscosity. Complex viscosity is defined as the sample's complex modulus divided by the measurement frequency. This viscosity may or may not equal to your sample's shear viscosity. When testing the a sample that is viscoelastic, especially if your material is more elastic than viscous, then the measured complex viscosity will not be equals to the shear viscosity that is measured under flow mode. Here is an example showing the relationship between the storage and loss modulus of a viscoelastic material. You drop a ball to the floor and watch for how the ball bounces back. The height that the ball can bounce back correlates to the energy storage, and the height that it gets lost correlates to the energy loss. How much energy was lost as heat during this bouncing action. But mathematically, storage and loss modulus follows this triangle relationship. And the phase angle is defined here. Tangent delta is defined as the loss modulus divided by the storage modulus. Here is a list of all the commonly used dynamic oscillatory test methods that you can use on your rheometer to measure the viscoelasticity property of your material. In Trios software, once you select Oscillation Test Mode, under the drop-down list, you will be able to see all of the available oscillation measurements that's on your instrument. In our today's course, we're going to specifically discuss 5 types of most commonly used oscillatory tests that you can use to measure your sample's property. Those methods include a dynamic strain sweep. In Trio software, it is called amplitude sweep, and then a dynamic time sweep, an oscillatory frequency sweep, temperature ramp, and temperature sweep. The first oscillation test method we're discussing here is the dynamic strain sweep test. If you are a Discovery Hybrid rheometer user, you can also program to do a dynamic stress sweep. Both strain sweep or stress sweep will give you the same identical results. A dynamic strain sweep test is an isothermal oscillatory test. You load your sample to the instrument, and then you oscillate your geometry using a constant frequency. During the measurement, you are varying your oscillation strain amplitude. You gradually increase the strain, gradually increase the strain. So through the measurement, you'll monitor your sample's modulus changing as a function of strain amplitude. This screenshot here is showing you in Trio software how to set up an oscillatory amplitude sweep test. One application of using this strain sweep experiment is to measure your sample's linear viscoelastic region. This test method can also be used to measure a sample's yield stress. For a more experienced rheology user, a strain sweep test is also used to measure nonlinear viscoelasticity property of a sample. That procedure is called LAOS, Large Amplitude Oscillatory Shear Test. Since that measurement is more advanced procedures, this is not going to be covered in detail in this course. Here is a typical example of a dynamic strain sweep results. From this measurement results, you can see that under low oscillation strain, stress and strain follows this straight line relationship. In this region, the measured modulus is independent of your applied oscillation strain. Again, for every single data point, you can see that the point graph shows the stress signal shows a very nice sinusoidal waveform. As you gradually increase your measurement strain up to a certain critical point, stress and strain start not following the straight line relationship. The stress curve starts to deviate from the straight line. In the meantime, the sample modulus starts to show a decrease. As you're getting further and further outside this critical point, as the strain is further increasing, Okay, the measured modulus shows a significant drop, and the stress curve is deviate more and more from the straight line relationship. As you monitor from the point graph, the output stress signal is not showing a sinusoidal waveform anymore, but exhibit a very weird shape. This area is outside the linear viscoelastic region of your sample, which means with this large amplitude oscillation, you have already irreversibly changing the structure of the material. Then, from a typical strain sweep experiment, how do we define this end of linear viscoelastic region? So a typical definition for end of linear region strain is by monitor how much the modulus decrease. If you observe a decrease in storage modulus for over 5 to 10%, that is the point, the critical point showing the end of the linear region of your material. All traditional oscillatory tests must be performed using the strain that's in the linear viscoelastic region. However, a sample's linear region is sensitive to the measurement frequency. Here is an example of performing strain sweep measurements on a PDMS sample using different measurement frequency. This result shows that if you perform the measurement using a low frequency, sample shows lower modulus, but it has broader linear region. The linear region ends at a much larger strain. If you perform the same measurement but using a higher measurement frequency, first of all, you see the sample shows higher modulus, means the sample is stiffer, but the linear region is ending at a much shorter strain. So if you're going to perform a frequency sweep test on this sample, you need to consider select a strain as in the linear region within your entire measurement frequency range. Secondly, sample's linear viscoelastic region is also sensitive to the measurement temperature. If you perform a strain sweep measurement on a sample that's under solid states, first of all, the sample will show higher modulus. That means the sample is stiffer. But when the sample is under solid states, it shows a much shorter linear viscoelastic region. If you heat the sample up to a higher temperature, the sample will melt or get softer. First of all, when you perform the strain sweep measurement, you see the sample shows lower modulus. But softer sample shows wider linear viscoelastic region. The linear region will end at a much larger strain. So if you're going to conduct a temperature ramp experiment on this particular sample, you need to consider select a strain that's in the linear region from both solid all the way to liquid states. You need to choose the strain in this area. For those experienced rheology users, if you are interested to perform nonlinear viscoelasticity measurement, specifically if you are interested in performing a LAOS testing, large amplitude oscillatory shear testing, then I would like to highly recommend you consider log on to TA Instruments website and take this free webinar given by Professor Garrick McKinley. We will not be discussing in great details about this part in our today's course. The second dynamic test we are introducing here is the dynamic time sweep. This is an isothermal oscillatory test. In the time sweep, you load your sample to the instrument, oscillate the geometry using one single frequency, for example, 1 Hertz. And then you are conducting an oscillation using a small amplitude that is within the linear viscoelastic region of your sample. Time sweep is commonly used to monitor sample physical property change as a function of time. Example of using this procedure is to monitor the sample curing or monitor sample stability against thermal degradation. Time sweep experiment is also used to study your sample's syncotropic behavior. Here is an example of using dynamic time sweep to monitor epoxy curing. We mix this two-component epoxy and load it to a rheometer. Then we started the time sweep measurements. At the initial time, you observe the sample loss modulus is greater than storage modulus. This tells you that the material behaves more like a liquid. Both moduli increase rapidly over time, and then up to a certain time, G' and G" undergoes a crossover. This is a transition of a sample going from liquid-like to solid-like. Some people consider this crossover point as the gel point of the material. After that, G' start to take over, which tells you the sample behaves more solid-like. Eventually, when the curing completed, both moduli will reach to a plateau. Here is another example showing how to use time sweep to monitor polymer melt thermal stability. This is a result of testing a high-temperature polymer PEEK at its processing temperature, which is 400 degrees C. This result shows that if you process the polymer under nitrogen atmosphere, the polymer remains relatively stable, so both moduli stays constant over the processing time. But if you use air as an processing environment, you can see that both moduli significantly increase during the time sweep. That tells you the polymer undergoes a molecular weight buildup, eventually a cross-links. Another oscillatory test method we're introducing here is a dynamic frequency sweep. This is another isothermal oscillatory test. You load your sample to the instrument and oscillate the sample using a small amplitude that is within the linear viscoelastic region of your material. During the measurement, you are changing your test frequency. You can oscillate the sample from very low frequency up to high frequencies, or you can also oscillate the sample starting from a high frequency and gradually slow down to low frequencies. As long as the amplitude you apply to the sample is within the linear viscoelastic region, whether or not you perform the frequency sweep from high to low or from low to high, the results should be identical. Frequency sweep test is very commonly used in varieties of industries. It provides you some very useful information. For polymer applications, frequency sweep test results helps to directly measure your polymer chain relaxation. For polymer melt frequency sweep measurements, the results can be used to correlate to polymers' molecular weight and molecular weight distribution. For measuring semi-solid materials like personal care product or lotions or shampoos, cosmetic product, the frequency sweep is also used to scouting the differences of viscoelasticity properties between different formulations. Here is an example showing a typical frequency sweep test results on polymer melts. And this is one of the standard test methods to evaluate the melt rheology performance following ASTM D4440. Directly from the frequency sweep test, you can correlate the results to the polymer's molecular weight and molecular weight distribution. If anyone who is interested in this topic, then I would like to recommend you consider log on to TA Instruments website and listen to this free webinar that is given by Professor Chris McCaskill. Frequency sweep is also commonly used as a typical QA/QC analysis method. The measurement results provide quantitative comparison on different formulations. Here is an example of testing 3 different lotions with different formulations. The measurement results that shows these 3 formulations exhibit significant differences in samples moduli. Another dynamic oscillatory method we're introducing here today is the dynamic temperature ramp experiment. In this test, the sample is oscillated using one single frequency, for example, 1 Hz, and is also oscillated using a small strain amplitude that is within the linear viscoelastic region of the sample. During the measurements, the temperature is changing linearly. You can conduct either a heating test or cooling test. a common heating and cooling rate is controlled at 1 to 5 degrees per minute. The uses of this type of measurements is to measure your material's linear viscoelasticity property as a function of temperature. This test method also allows you to measure your sample's glass transition and also subambient transitions. The screenshots in here shows an example of how to set up a dynamic temperature ramp experiment in TRIOS software. Here is one example showing the dynamic temperature ramp test results on a polymer ABS sample. From these measurement results, you can monitor sample modulus, storage and loss modulus change as a function of temperature. Also, a glass transition is observed at temperature around 100 degrees C. In addition to performing a temperature ramp experiment, one can also consider to design a temperature sweep or step test. In this measurement, the temperature is changing stepwise. The instrument jumps to one measurement temperature, hold there for a certain amount of time until the sample is further totally equilibrated. At the end of the equilibration, you can either design to perform a single frequency measurements or conducting a frequency sweep at the end of each equilibration. This temperature sweep experiments also allows you to measure your material's viscoelasticity property as a function of temperature. If you're conducting a temperature sweep in combination with frequency sweep experiment, the testing results will allow you to perform the temperature superposition analysis on your polymer sample. So what is time temperature superposition? When study the rheological property of a polymeric material, you will see that the rheological property for the polymer that you measured as a function of temperature is almost like a mirror image that correlates to your material's rheological property measured over a really wide range of frequency. The inverse of frequency is the time. So this is what typically people call the time temperature effect. From the range of the frequency, you understand that there is not possible that you can use one single frequency sweep to get the data over such a wide range of frequency. In order to obtain your sample's rheological information over such a wide range of frequency or long time scale, you need to perform a time temperature superposition analysis. So in order to program that test, you need to design a test that is called dynamic temperature sweep / frequency sweep. From that test results, you can use the software to extrapolate the data to obtain a results like this. So far, we have introduced all of the commonly used oscillatory test methods to evaluate the viscoelastic property of a material. In this last section, we would like to introduce two commonly used transient test methods, which are stress relaxation and creep recovery test. A stress relaxation experiment is conducted by applying a strain to the sample instantaneously and hold constant with time. During the measurement, stress is monitored as a function of time. In a stress relaxation test, relaxation modulus is defined as the stress that's changing as a function of time divided by the strain that you applied to the sample. The screenshots here is giving you an example of how to set up a stress relaxation experiment using TRIOS software. When you perform stress relaxation experiment on a purely elastic material such as a spring, here is the change of the stress curve you will observe. Once you apply a strain to the spring will immediately respond with a certain stress. As long as you hold the strain constant, the stress is holding constant as well. There is no relaxation. If you perform a stress relaxation experiment on a purely viscous material such as water, once you apply a strain, simultaneously the sample will respond with a certain stress, but this stress will relax to zero in an extremely short time. If you perform stress relaxation to a viscoelastic material, such as silly putty, the stress relaxation curve will look like this. If this polymer is linear, eventually the stress over time will relax down to zero. Here is an example showing the stress relaxation test results on a linear polymer, polydimethylsiloxane. The measurement was conducted using a 25 mm parallel plate, and the strain was set at 5%. During the measurement, the sample's relaxation modulus change as a function of time is plotted in this graph. Since this polymer is linear, so eventually the relaxation modulus will reduce down to zero in theory. The second transient experiment we're introducing here is creep recovery. Creep is inverse to stress relaxation. In the creep test, stress is applied to the sample instantaneously and held constant for a certain period of time. During this time, the changing of sample strain is monitored and recorded. In the recovery zone, stress is released to zero, and from there, the changing of strain is continuously monitored over a long time to observe how much strain can get recovered from the creep test. In the creep test, creep compliance parameter is defined as the strain that is changing as a function of time divided by the stress you apply to the material. This screenshot here is showing you an example of how to set up a creep recovery experiments in Trails software. When you perform a creep recovery experiment to a purely elastic material, such as a spring, this is the kind of strain response you are expecting to see. When the stress is applied to the spring will simultaneously respond to the stress with a certain percentage of strain. As long as you hold the stress constant, the strain is holding constant as well. When you release the stress to zero, instantaneously the strain will recover 100% and reduce down to zero. When you perform a creep recovery experiment to a purely viscous sample, such as water, as the stress is applied to the sample starts to flow. So you will observe the strain will start to change in a linear motion. When you release the stress to zero, the strain will stop at the very last data point as the stress was on the sample, which means when testing creep recovery measurements on a purely viscous material, you will achieve zero recovery. So here is the data that shows when you perform a creep recovery experiment on a viscoelastic material. So as you apply a stress to a viscoelastic sample, simultaneously you see the sample jump to a certain strain. This part of the strain correlates to the elastic behavior of the material. Gradually, the changing in strain curves off and eventually it reaches to a straight line relationship. So when the strain change follows this straight line curve, that tells you that the sample is already reaching steady state. This portion correlates to your sample's viscous response. In the recovery zone, when you release the stress to zero, simultaneously you see there's a certain amount of strain that is recovered. And then the recoverable strain starts to curve off, eventually reach to a plateau. So once the strain change becomes constant, that means there is a certain amount of strain which cannot be recovered. Creep recovery experiment is very commonly used to measure samples' viscoelastic properties. In the creep test, the simultaneous jump in strain is correlates to the elastic response of your material. And when the strain change follows a straight line relationship, the slope of the straight line equals to the stress you apply to the sample divided by your sample's zero shear viscosity. In the recovery zone, the amount of strain that can be recovered is directly correlates to your sample's elasticity. If you can achieve a lot more recoverable strain, that means this sample is more elastic. If you are not able to achieve more recoverable strain, if you have less strain recovery, that means this sample is less elastic, is more viscous. So the recovery zone is very sensitive to differentiate sample's elasticity. Here is an example showing a creep recovery measurement results of a good and bad paint sample. This measurement is also commonly used to evaluate the viscoelastic property of polymer melts. Before we end today's training, I would like to show you where you can find the help documents. Once you install Trio software to your computer, you should be able to find this icon from your computer desktop. Double-click on this icon, you will open TA Instruments help manuals. From this menu, you will find a lot of getting started guide on how to use the instrument or some specific accessory. When open Trio software and double-click on this big question mark, you will activate the Trio's online help. Use this online help, you can find a lot of related topics regarding how to set up experiment and how to use a specific geometry. For a quick search, you can simply type in some keywords to get to the topics that you are interested in. Other than today's Theory and Applications course, you can also find some web-based e-training courses from our website. You can find the e-training courses on Aries G2, e-training courses on Discovery Hybrid Rheometer, and also Trio software. Those e-training courses are mostly focused on teaching people how to operate the instrument and also how to use the software. There are also a series of practical training courses on our website, which include thermal, rheology, and also microcolorimetry. Those courses are mostly focused on talking about the thermal rheological measurement theories. In addition to training courses, you can also find a lot of free webinars from TA Instruments website. Many of those webinars are given by professors from different universities. Those professors are doing research work. They are specialized to rheology from different areas. Some other useful information you can obtain from our website include tech tips and applications note papers. From our website, you should be able to find hundreds of very helpful tech tips. Those tech tips are short YouTube videos teaching people how to use a certain geometry, how to operate the instruments, or how to set up a specific test. Also, in the applications note library, by searching keyword, you should be able to find a lot of useful short papers on specific subject. For example, if you type in rheology, you should be able to find hundreds of applications papers talking about rheological analysis on different kinds of material. Also, from our website, you can find a series of different seminars on different topics. With that, I would like to end this training course for today. Thank you very much for attending this course, and I hope you find it informative. All of your questions can be submitted to this Rheology Support Hotline email. You can also download the content of this presentation from this website. Please do not forget to watch part 2 of this course, which will be talking about rheology applications. We also have some other online training courses on TGA, DSC, and DMA. Again, thank you everyone for attending the training course today, and have a great day.